So I got this shiny poNYta in Legends Arceus, and it got me thinking, what makes anything shiny? Yeah, that's my intro. Is that okay? Oh yeah, it's my video.
We know we can see things because of electrons moving up and down their positions in an atom. What does that mean? We excite the outermost electron with a photon, fancy word for a piece of light, and as does everything else, that excited electron wants to come back to stability. It wants to come back down to its original position. To do that, they have to get rid of the energy they absorbed from the photon. The color we observe depends on the distance between the electron's initial and final positions.
So what's the difference between something shiny and something dull?
Well, for materials like metals, the outer electrons are strongly held to the positive charges in the nucleus. Notice that in the periodic table, across a period, metals have smaller atomic numbers. This means less positive charge in the nucleus and therefore a weaker attraction towards the outermost electron.
So when you have multiple metal atoms, those loose electrons can move around, neighbor atom to neighbor atom.
Now, what happens when you place any atom with another is that you're changing the energy levels of the electrons present.
How does that happen?
We start with one electron in the positive nucleus, and we know they experience an attraction. We add another atom with its own electron and its own positive nucleus, and there are attractions between opposite charges and repulsions between same ones.
When you consider all of these, we expect the electrons to have different energy values, because unlike in the first setup where there's only one interaction,
this time there's three. This one electron is only dealing with being attracted to the positive nucleus, while this one here is dealing with attractions with two nuclei and repulsions from another electron. You can see how much more energy is required to be this other electron. Add more and more atoms and we end up with electrons having these so many energy values.
Now what I haven't told you is that for every energy level we talked about earlier, there is a counterpart energy level of a higher value.
When electrons absorb energy from, let's say, light, these are the positions they can go to with that added energy. So when we were adding the energy levels from before, we were also adding these higher energy levels.
Up until the point where there's enough atoms, the energy levels could come out like these, depending on the material.
For metals, the lower and higher energy levels appear as if there's no difference. They're all just energy levels. It's easy to move an electron from here to here, or here to here, or here to here.
Now for non-metals, often there's a huge-ass gap between the two sets of energy levels.
A consequence of this is that non-metals are more selective with the kind of light that they can absorb, because there are only a few limited options for an electron to go to. Compare that to metals, where basically any kind of light can get absorbed and re-emitted. Unlike for picky non-metals, some of the light would just pass through instead of reflecting. That's what shiny is. It's basically more light, sure, but what does more light even mean is the point of this video.
And the cool science doesn't stop there.
As we go towards heavier atoms, Einstein's relativity starts to be more noticeable.
In addition to an electron's energy level, the electron's position is also important to how the overall material behaves.
And that has something to do with why some metals have colors and some are just silver.
I explained that in my next video, and as usual, thanks for watching. I'll see you next time.